Alright, silly people, here's the situation. We are going to be doing stuff with an M matrix now rather than an S matrix like we did in the last problem, because apparently it's more useful in some cases, according to Griffiths. I don't know about that, but we'll see. So the first part is actually to find the elements of M matrix in terms of the elements of the S matrix, and we're going to be able to do that if we expand these couple linear equations out into four separate equations. So equation 1 is going to be F equals AM11 plus BM12, and G, or the equation 2 is going to be G equals AM21 plus BM22. And then equation 3 is now the expansion of the S matrix linear equation. So it's B equals AS11 plus GS12. And then equation 4 looks like F equals AS21 plus GS22. Why is this useful? So the first thing that we're going to do is we're going to solve equation 3 for G, right? So B, or actually let's just go ahead and solve it quickly. G equals B minus AS11 all over S12. This is useful because equation 2 also has equal to G, so we'll just set this equal to equation 2. So we get B minus AS11 over S12 is equal to AM21 plus BM22. So just comparing the stuff that's attached to the constants on either side, on the left-hand side, B is attached to 1 over S12, and on the right side, it's attached to M22. There's an equation. And then also see that on the left-hand side, A is attached to minus S11 over S12. And on the right-hand side, A is attached to M21. There's another equation. Then now we can just set 1 equal to 4, which is going to allow us to get the other two elements. So because they're both equal to F, we're just setting AM11 plus BM12. And then on the right-hand side, it's AS21 plus S22 times G, but we have a specific form for G, which is B minus AS11 all over S12. Simplifying the right-hand side a little bit, we've got A times S21 minus S11 S22 over S12 plus B times S22 over S12. Cool. Comparing the constants. So on the left-hand side, we've got M11 attached to A. On the right-hand side, we have S21 minus S11 S22 over S12. That's an equation. And then on the left-hand side, B is attached to M12, while on the right-hand side, it's attached to S22 over S12. Kind of crazy. So now we can construct M, the entire matrix. Just do it here. M is going to be equal to M11 was S21 minus S11 S22 over S12. M12 was S22 over S12. M21 was minus S11 over S12. M22 was 1 over S12. Fantastic. If you factor out 1 over S12, something magical happens. So now you have S12, S21, minus S11, S22, minus S11, S22, and 1 down here. That stuff in the top left element is just minus the determinant of S, because it's 1 over S12 minus determinant of S, S22, minus S11, 1. So pretty nice, right? Now we got to do the same thing backwards. So we're going to get s in terms of m now. So let me copy down the same equations that we used before and just do something slightly, ever so slightly different. We're basically going to be doing the operations in reverse. Right. So first step now is to solve 2 for g. No, solve 2 for b. Let me write that down. 2 for b. So you get b equals m2. Nope, it's g minus a m21 over m22. And then set this equation now equal to 3. So a s11 plus g s12. And then comparing stuff attached to g on the left-hand side, we've got 1 over m22. On the right-hand side, we've got s12. There's an equation, a really gross-looking polygon. And then the stuff attached to a on the left-hand side is minus m21 over m22. On the right-hand side, it's s11. There's an equation. Then we got, just keeping going, we're going to set 1 equal to 4 again. So on the left-hand side, we have a plus m12 times b, and also a has m11 attached to it. There's a cat butt in my face. And then, but we have a specific form for b, so it's g minus a m21 all over m22. And on the right hand side, we just have as21 plus gs22. Simplifying the left hand side, we have a times m11 minus m21 m12 all over m22. And on the g stuff, it's just m12 over m22. So we can now compare stuff attached to a on the left-hand side. m11 minus m21 m12 over m22. On the right-hand side, it's attached to s21. That's an equation. And on the left side, g is attached to m12 over m22, while on the right, it's attached to s22. There's the last equation. So we can construct s in full now. So we've got minus m21 over m22, 1 over m22, m11 minus m21 m12 over m22, and m12 over m22. Again, factoring out a 1 over m22 gives you something magical. So you get 1 over m22 times minus m21 up here. Now the bottom left term is equal to the determinant of m. And then we get 1 on the top right and m12 on the bottom right. Whatever. So that's part A done. Cool. Part B, or no, that's not even part A done, because now we need to express RL, TL, RR, and TR all in terms of M elements. But we already kind of have all we need. So from the last problem, RL was equal to the mod squared of S11, and we already know what S11 was. It's minus M21 over M22. So this is just going to be the mod squared of M21 over M22. Not that crazy. Then RTL, well, we'll do that one next, is the mod squared of S21. So it's the 1 over m22 determinant of m in a mod squared. We can leave it just like that. Then r is s22 squared. So it's the mod squared of m12 over m22. And then finally, r, or tr down here is equal to the mod squared of s1, 2. So 1 over the mod squared of m2, 2. I guess I better write it. It's s1, 2 squared, right? Fine, okay, so now we can move on to part B. Suppose you have a potential consisting of two isolated pieces, and then it shows you a nice little figure that Griffiths drew of two isolated potentials in a one-dimensional frame. So this is your one dimension. I'll draw the potentials. One of them kind of goes like and then the other potential goes like it doesn't matter how well you draw them. This here is supposed to represent a zero potential region. Also here is zero potential, and also on this little back half here, the potential is 0. I can write what the wave functions are in each range is, right? So the first wave function is going to look like a e to the ikx plus b e to the minus ikx. So region 2's wave function is c e to the ikx plus d e to the minus ikx. And then finally, in the third region, it's f e to the ikx plus g e to the minus ikx. Right? Kind of crazy. So that's all that is supposed to like symbolize is that A represents particles coming in from the left, B represents particles exiting the potential from the right, C represents particles that have made it through the first potential, and then D represents particles making it from the second potential. F is particles exiting the second potential, and G is the particles that are coming in from the right of the second potential. Right? Okay. So there is an M matrix for this guy, which is going to obey the equation AB equals, oh, that's not even right. It'll be CD equals the transfer matrix times AB. And on the right, there's another matrix which obeys the equation FG equals M2 times CD. If you happen to want to express FG in terms of AB, then you can just use the expression for CD from this equation over here. So you get M2 times M1 AB, and there you have it. You now have an equation which represents the total transfer matrix between the two potentials, where now M is equal to M2, M1, which is what the proof was asking for. Kind of silly. Then it says, part C, construct the M matrix for scattering from a single delta function potential at point A. We already know the wave functions for this as well. It's I'll say the potential first. It's minus alpha delta x minus a. So it's going to take the form as any other delta function, wave function. So it's in the first region, so to the left of the potential, we're going to have a e to the ikx plus b e to the minus ikx. And to the right of the potential, we're going to have f e to the ikx plus g e to the minus ikx. The relationship between the constants, though, is found by doing the boundary conditions. So the first boundary condition is that they are continuous at the boundary, which is at A for this potential. So we have the equation a e to the ika plus b e to the minus ika equals f e to the ika plus g e to the minus ika. It's really useful to solve this equation for f times e to the 2ika. So we have f e to the 2ika. We're just multiplying the whole equation by e to the 2ika. So we got a e to the 2ika here, plus b minus g. Cool. Let's call that equation 1 now. The other boundary condition is a discontinuity at the boundary. So it's going to go something like psi to the right, the derivative of that at a, minus the derivative of psi to the left at a is going to equal minus 2m alpha over h bar squared k times psi to the left at a. That's the discontinuity condition. So just doing the derivatives real quick, we've got ik times f e to the ika plus, or actually now, minus g e to the minus ika minus ika e to the ika minus b e to the minus ika equals minus 2m alpha over h bar squared k a e to the ika plus b e to the ika. Also, we're going to solve this equation for f times e to the 2ika. So we're going to multiply the whole equation by e to the ika, and I even think this k isn't supposed to be here for the discontinuity condition I just remembered. So there's that, and we're also going to divide the whole equation by ik. So we get f e to the 2ika minus g minus a e to the 2ika plus b equals minus 2m alpha over h bar squared ik, and then times a plus, or actually it's a to the 2ika plus b. That's it. Okay, now solve this for f e to the 2ika. So let's just stick an equal sign here. This will become plus, this will become minus, this will keep its sign. Glorious. Now, this is going to be our equation 2, and we're going to add equation 1 with equation 2 first. That's going to give you 2f e to the 2ika on the left side. And on the right side, the g's cancel out, the b's cancel out, but the a's add up. So you got 2a e to the 2ika minus 2m alpha over, let's actually stick the I up top, because why the hell not, times a e to the 2ika plus b. Now this is pretty crazy. Let's cancel out 2's on either side. All of this stuff depends on 2, and let's define a quantity known as beta, which Griffiths also does quite a bit. So it's m alpha over h bar squared k. And solve this for f. So just putting all the exponential stuff on the b term now, it's going to be f equals a plus I beta times a plus b e to the minus 2ika. If you split this up into stuff dependent on a and stuff dependent on b, it's a times 1 minus, or 1 plus I beta plus b I beta e to the minus 2ika. Now, I know an equation which relates f to a and b through a transfer matrix, and it's this one way the hell up here. So let's use that to get the first couple elements of our transfer matrix, shall we? Pop. Oh, the equation didn't get carried over all the way. But yeah, looks like M11 equals 1 plus I beta and I beta e to the minus 2 ika looks like M1 too. We're making great strides in finding the transfer matrix. We'll find the other two by subtracting equation 2 from equation 1. So now we have, just looking back at the equations, should be 0 on the left-hand side because the f stuff will cancel out. The a e to the 2ika stuff will cancel out, but the b's will add up, so we'll have 2b, and the g stuff will add up, so we'll have minus 2g, and then we'll still have the plus 2 beta 2, oh no, it's minus 2I beta. Yeah. Times, what was it? A e to the 2ika plus b. Sure. So now let's cancel the 2's out. And then just use this to solve for g, I think. So we'll get g equals b minus I beta a e to the 2ika plus b. And we'll split it up into stuff dependent on b. So we'll get b 1 minus I beta plus a, or actually it's going to be minus I beta a e to the 2ika. And I know an equation which relates g to b and a through elements of the transfer matrix way the hell up here. It's this one. Guys, we're so funny right now. We're using equations. Stick that guy right there. So it looks like, whoops, A, or M12, I guess, no, M21, is minus I beta e to the 2ika, and M22 equals 1 minus I beta. So we have all of the equations now to get the elements of M. So let's put it all together. M is going to be 1 plus I beta up here, and then I beta e to the minus 2ika up here, I beta e to the, or it's minus I beta 2ika down here, and 1 minus I beta here. Cool. That's kind of gross. But yeah, now part D is looking like, by the method of part B, find the M matrix for scattering from the double delta function. That is a potential that has the form of minus alpha delta x plus a plus delta x minus a, right? We can split this up into two potentials. That's why he's suggesting we use the method from part B for this, because the scattering matrix for this part of the potential is going to be the same as the scattering matrix for this part. So that's going to be our M2, because it's going to be to the right of this scattering matrix. For this scattering matrix, the only thing that changes about the potential is now it's set up at x equals minus a rather than x equals a. So it looks like the other thing that's going to change are the signs of a. So M is going to be M2M1, yeah, M2N1, where M2 is going to be this guy up here, which we haven't changed yet, I beta e to the 2 minus 2ika, 1 minus I beta. And then this guy is going to be the same matrix, but anywhere an A shows up, we're going to flip the sign of the stuff that's attached to it. So there's a minus sign in the exponential up here, but a plus sign in the exponential up here, but this stays the same. Okay, now we have to do the most god-awful matrix multiplication you've ever seen. So it's 1 plus I beta squared plus, and it's actually, yeah, plus beta squared e to the minus 4ika up there. Then we got 1 plus I beta times I beta e to the 2ika plus 1 minus I beta times I beta e to the minus 2ika. And then down here we got 1 plus beta, or 1 plus I beta times minus I beta e to the 2ika plus 1 minus I beta times, and this is also a minus sign, I think. Yeah, this is going to be a really cool expression. I beta e to the minus 2ika. And then down here, we're just going to have 1 minus I beta all squared plus, that's actually the second part of the thing. The first part of the thing is positive beta squared e to the 4ika minus, or actually plus 1 minus I beta all squared. Okay, this is going to get simpler by a lot, I think. 1 plus I beta all squared goes like 1 plus 2I beta plus beta squared, or minus beta squared actually. My bad, but it's still added on to beta squared e to the minus 4ika. Down here we've got minus I beta e to the 2ika plus beta squared e to the 2ika minus I beta e to the minus 2ika plus beta squared e to the minus 2ika. That's a lot of terms. Up here we're going to have I beta e to the 2ika minus beta squared e to the 2ika plus I beta e to the minus 2ika minus, or now this is going to be plus beta squared e to the minus 2ika. I hope I did all of my signs right. Because God help you if I didn't. This is going to be plus 1 minus 2I beta plus beta squared. No, still going to be minus beta squared, actually. Okay. Funny stuff. In the top left, we can split it up into stuff which depends on 1 and stuff which depends on 2I beta, and also plus beta squared e to the minus 4ika minus 1. I think that's as good as it's going to get. On the bottom, we've got a couple of things. So we've got minus I beta times e to the 2ika plus beta squared times, or actually, let me add the other term before I get all fun and fancy free. It's going to be minus I beta plus e to the minus 2ika plus beta squared times e to the 2ika plus e to the minus 2ika there. And then up here we've got I beta times e to the 2ika plus e to the minus 2ika plus beta squared. I think I did mess up a minus sign somewhere. And I did, because this should have a minus sign on it here. So this will be a minus sign here. My bad. But then, yeah, this is beta squared. And then we've got e to the minus 2ika minus e to the 2ika. And then down here we've got beta squared times e to the 4ika minus 1 plus 1 minus 2I beta. Gross. I don't really see any more reason to simplify it. You can if you want, obviously, um, but you really care about the transmission coefficient for the potential. Um, and the transmission coefficient here, because it's going to just be equal to the TR. TR, remember from the last problem, is S12 squared, but we already found that that's equal to 1 over mod squared of M22 from a part before this. So all we really need or care about is this element down here. So without simplifying further, I'm so sorry about that. We're going to have 1 over the mod squared of beta squared e to the 4ika minus 1 plus 1 minus 2I beta. So let's just do the inverse of this equation before things get hairy. So we're doing the mod squared, so we're going to do the stuff dependent on the complex conjugate guy of this times, that is the worst plus I think I've ever seen in my whole life, times the regular version, so beta squared e to the 4ika minus 1 plus 1 minus 2I beta. Cool. Just expanding that multiplied stuff, we're going to have beta to the fourth e to the minus 4ika minus 1 times e to the 4ika minus 1. I really don't need this parentheses here, actually. Plus beta squared e to the minus 4ika minus 1 minus 2I beta cubed e to the minus 4ika minus 1 plus beta squared e to the 4ika minus 1 plus 1 minus 2I beta plus 2I beta cubed e to the 4ika minus 1 plus 2I beta minus, and it's going to be plus actually 4 beta squared. Kind of crazy. So this 2I beta cancels this one out. The 1 is going to stick around. Let's try to expand this, though, because it's going to be beta to the fourth times 1 minus e to the 4ika plus e, or also minus here, actually, minus e to the minus 4ika plus 1 plus, let's group together the beta cubed stuff. Beta cubed stuff is fine. 2I beta cubed times, e to the 4ika minus 1 minus e to the minus 4ika plus 1. These 1's cancel out, that's fun. Plus beta squared stuff, e to the 4ika minus 1 minus, actually plus e to the minus 4ika minus 1. Cool stuff in there, right? Yeah, okay. Plus 1 plus 4 beta squared. I should write the 4 beta squared in here. Plus 4 plus 1. Okay, that's some funny stuff in there, dogs. So looks like we've got beta to the fourth, 1, or actually the 1's add up, so 2 minus, and I'm going to group this together in a really kind of silly way, but it's going to be 2 times the fraction 1, or e, to the IKA plus e to the minus 4 IKA over 2 plus 2I beta cubed. Again, I'm going to be suggestive and go ahead and move the 2I down here actually. So minus sign, or that's not even true, plus 4 with a minus sign because I'm moving the I to the negative. But then we're going to have e to the 4IKA minus e to the minus 4IKA over 2I plus beta squared. The ones will add up and it'll make 4 minus 2, which is 2, plus 2 times the fraction e to the 4IKA plus e to the minus 4IKA over 2, all plus 1. Funny. So this is the expression for cosine of theta, or cosine of 4Ka, I guess. This is the expression for actually minus the sine of 4Ka, I think. This is the expression for cosine of 4Ka. So we really have beta to the fourth, 2 minus 2 cosine 4Ka minus 4 beta to the third, are actually with a plus sign now because it's minus minus sine 4Ka plus beta squared 2 plus 2 cosine 4Ka plus 1. This is really funny because now we get to use some trig identities. So trig identity number 1. Did you know that sine of 2 theta is equal to 2 sine of theta cosine of theta? Also, did you know that cosine of 2 theta is equal to cosine squared theta minus sine squared theta? Yeah, this problem is actually pretty heavy on the algebra side. Let's just plug this form of the equation in to both places on the transmission coefficient equation. So we got beta to the fourth, all times 2, 1 minus, it'll be cosine squared 2Ka plus sine squared 2Ka plus 4 beta to the third sine, and I'm going to actually use this guy for that term, so it's going to be 8 beta cubed sine 2Ka cosine 2Ka plus 2 beta squared. Let me move this term down here so I don't get crowded up. Times, oh no, times 1 plus cosine squared theta minus sine squared, but it's 2Ka, not theta, so 2Ka minus sine squared 2Ka, all plus 1. Rightio, 2 beta fourth, 1 goes like cosine squared plus sine squared. So here, the cosine squareds cancel out, so you get 4 beta cubed, or beta fourth, sine squared 2Ka plus 8 beta cubed sine 2Ka cosine squared 2Ka plus 2 beta, and then here 1 again goes like cosine squared plus sine squared. So here the sine squared terms cancel out, so you get 4 beta squared cosine squared 2Ka, and it's all plus 1. Now this is pretty cool because if you factor out a beta squared and a 4, this is just going to be the square of a silly little combination of sines and cosines plus just cosine 2Ka, right? That's funny, so that in your transmission coefficient is 1 over that. Bitches. This problem took me way too long. I think I'm gonna go lie down.